We're going to do one final lecture on solving ax equal to b, and thus far what we've done is we've solved ax equal to b with Gaussian elimination. We've also done LU decomposition. And now I'm going to talk about quite a different way to solve ax equal to b, and these are called iterative techniques, iterative methods for solving ax equal to b. You can find more details about the course. This is a lecture for the course Beginning Scientific Computing. There's a link in the description to the course website, which is here, and you can check out more there where I have lots of notes and codes and so forth. All right, so let's talk about iterative methods. This is actually kind of a surprising way. If you've never seen this before, you'll find this kind of very interesting as a solution technique and also a bit surprising. So let's think about a 3x3 system of equation. And I want to solve this, so I'm thinking about solving ax equal to b, and here is the particular way. We've written this here not as ax equal to b in linear algebra form, but more just as three equations, three unknowns, and I've written out the equations explicitly. So what we're going to do with this in solving this is from the first equation, I'm going to solve for x. For the second equation, I'm going to solve for y. For the third equation, I'm going to solve for z. What do I mean by solve for x, y, and z? So the first equation, I'm going to just put x on the left-hand side all by itself. That means moving the y and z over to the other side, dividing by 4. And similarly for the second equation, solving for y, I want to isolate it. I didn't solve it in the sense that I don't know what x and z are. Same thing with the final equation, z, solving for z, I don't know what x and y are. But I'm going to isolate each one of these variables individually, and then we're going to set up an algorithm to actually look for solutions for this. So if I do that, here's what I get. So what you're seeing here is here's x, here's y, here's z, and I've isolated each one, and of course I don't have a solution because these are a 3x3 system of equations, right? I have to solve them all simultaneously. But what I'm going to do now with iterative methods is I'm going to basically now construct a for loop. And here's what the for loop is going to do. I'm going to start off with guesses to what the values of x, y, and z are. If I don't have a good guess, you could just pick 0, 0, 0. Right? So pick a guess and you put it in here. And what we're going to do is construct an iterative procedure. And here's the iterative procedure. X of k plus 1 is equal to 7. And then notice on the other side, 7 plus y sub k minus z sub k over 4. I just simply took this set of equations, and on the right side are the current values of x, y, z, and on the left side are some updated values. Okay? That's what this means. So I start off with some, at the kth iteration, it gives me the k plus 1 value. So remember, when you guess it, you're going to give it the first iteration numbers. You're going to say, okay, x of 1, y sub 1, and z sub 1 are some numbers. They could be zeros, which allows me to take these formulas and produce x2, y2, and z2. From x2, y2, z2, I can produce x3, y3, z3, and so forth. I can just iterate forward. Okay? So a pretty simple algorithm to write, actually, for the iterations. And actually, here is how the algorithm would go, right? You start off with some initial guesses. And if you don't have a good guess, just pick 0. Say, I'm going to guess all the values of these are 0. And of course it's not right, but you just guessed it, and then what you're hoping will happen is, as you iterate forward, that you might actually in fact converge to the solution. Okay? So then we're going to iterate what's called a Jacobi scheme, and that's what I just wrote down. The Jacobi scheme is my next value of x, y's, and z's are a times x of the current values. So that's this iteration algorithm right here. Okay? So now this is sort of some kind of matrix A, taking me from the current values of x and y's and z's to the next values of x, y's, and z's, which are here on the right-hand side. Okay, so I'm going to do this and just put it in a loop, a for loop, and keep iterating, and I'm going to check for convergence. So if I find that in fact the iterations start to converge, in other words, the next guess is very close, the next value of x of k plus 1 is within some tolerance of x of k, in other words, this converges to some value, I'll stop this iteration and check what I have there. Essentially what I've done is converged to a solution through this iteration scheme. In fact, here's what's kind of remarkable. I take this thing and I'm going to start off with some guesses. Here I start off with the guess 1, 2, 2, which is not the solution to that linear system of equations I started with. After one iteration, I've changed values of x. So from this x of 0, I can produce x of 1. From x of 1, I can produce x of 2, and so forth, right? So here are the values of what's happening to the x's, the y's, and the z as I iterate. By 15 iterations, notice where I am. 1.999993, 3.999985, 2.99993. And then after 19 iterations, I'm pretty much to numerical precision here, or format long E, 2, 4, 3, which is in fact the solution to that system AX equal to B. So simply by setting up this iteration procedure and starting with some guess, this thing actually converges to the actual solution of AX equal to B. Okay, this is called a Jacobi iteration, and this is actually quite remarkable that this works, right? This is a kind of a fun way to solve linear algebra systems because I didn't have to do any substitution or elimination. I just simply pick some guesses and let this thing iterate, and it gets me to a solution. Okay, so that's pretty nice. And in fact, here's some code in both MATLAB and Python to execute this. So these are very simple codes, and I can start off here, for instance, x, y, and z in Python, and I'm going to start off with 0. MP array 0, MP array 0, MP array 0. So this is the x, y, and z values, and I'm going to go in this loop for j equals 1, j in range to 100. So it's going to go through this loop up to 100 times. Okay? And in fact, it's never going to go 100 times because I'm actually find the solution well before that, and I have an if statement here telling me if I find the solution to get out. Okay? So first of all, this code actually highlights something interesting, which is MATLAB is very efficient at dynamic allocation of memory. So in other words, you can just keep building vectors and increasing their size very easily, whereas in Python, you have to actually use the append functionality, np append. So I take my current value of x, and here's what I'm going to add to it. Notice, this is my formula. 7 times y of j minus z of j over 4. I update y with 21 plus 4x plus z over 8, and then I append the value of z with 15 2x minus y. Okay? So by the way, this is just executing this here. This is exactly what we're doing. I update x according to this right-hand side, update y according to this right-hand side, update z according to this right-hand side. So that's what you're looking at in this code is these updates, and I use append to add on to the vector that I already have. So I'm just in this loop, going through this, appending values, and then I ask the following question. If the absolute value of x of j plus 1 minus x of j is less than some, 10 to the minus 5, break out of the loop. What I really should do here, and I just did it for economy, I didn't do all three, I should check that x, y, and z are all converging, okay? But that's it. That's the Python loop that will allow you to do just Jacobi iteration. So it's very efficient and fast, and it converges within, I just showed you, 20 iterations. The MATLAB equivalent of this is here. I give it some guesses. There are the guesses. Zeros, and then I just update. And now what I'm going to actually do in MATLAB is the same thing, make a vector of all and keep track of all the guesses. So I start off at 0, and starting from x of 1, I can produce x of 2, y sub 2, z sub 2, and then from z sub 2 produce x of 3, y sub 3, z sub 3, and so forth. So here's my iteration scheme. This is equivalent to what's going on right here, and then I just have the if statement. If x is converging and y is converging and z is converging to some tolerance, break. Okay? So both of these algorithms will basically converge, just like what I'm showing you here on this table. It'll just start off, here I've used a different guess, but it's going to do the same thing here. You're going to start iterating, you're going to start producing a vector of x values, a vector of y values, and a vector of z values. Of course, you don't have to produce a vector. You could just simply produce the last value, and who cares about it, all the rest of it. But if you produce the vector, you can see the entire structure of how it's actually iterating and the changing values of x as it converges to the solution. So these codes here both produce vectors which allow you to track how well it's converging to the solution and how quickly. Okay? And so once it's converged, you're done. You have the solution to this thing. So this is quite remarkable, right? Because we don't have a theory for this, right? For Gauss elimination, or LU, we had a very structured argument. This was about elimination. It was about substitution. Here we're just setting up an iteration scheme, letting it go, and it gets us to the solution. Okay? I remember the first time I learned about this, I thought, wow, this is amazing that I'm not using any other information except I'm just making up some random scheme, it seems, and starting off some initial conditions, and this thing actually converges to the solution. So in fact, you might be get carried away with this. You might think, hey, I can do this with anything. So let's just redo this same calculation, okay? But now what I'm going to do is I'm going to switch the first and third rows. They're the same governing equations. All I did was I switched the first and third row. And so we're going to do the same thing we did before. I'm going to go ahead from the first equation, solve for x. From the second equation, solve for y. From the third equation, solve for z. And with those, I'm going to make an iteration scheme. And here's the iteration scheme. So it's exactly what I did before. And what we know is it should not matter whether you switched the equations, the rows of the equations, right? They're the same governing equations, but I do get a different iteration scheme. And here's what happens when now I run this through the code. I start to iterate, and in a very short time, look what happens to the values. They start to grow. In fact, if I keep going, this code produces plus or minus infinity values for all the x, y's, and z's. So this thing blows up. It's the same system of equations. I set up the iteration slightly different. And in one case, I got it to converge to the answer. In this case, all these values are going to plus or minus infinity. So this thing is kind of worthless. So the question is, when does this thing actually work? Because it's concerning that you took a system of equations and it seemed arbitrary that it worked with one formulation, and I switched the rows and it doesn't work anymore. So here's the theoretical underpinning of when you can get this to work and when it does not work. It's called the idea of strict diagonal dominance. And this is a really important concept for iterative schemes, which basically, to have strict diagonal dominance, you take the diagonal term of, let's say, the kth row, you take its absolute value. If it's bigger than the sum of all the other elements in that row, then it's strictly diagonal dominant. And in fact, if it's strictly diagonal dominant, you're guaranteed that this will converge to the solution of ax equal to b. So what you're really looking for is this structure to be holding place. So you look at the diagonal term and you want it to be bigger than the sum of the absolute value of the rest of the terms. If that is, you know that the iteration scheme will work. It's guaranteed. Okay? If it's not, it doesn't mean it won't converge, but there's no guarantees it will. So generically, you can think that you should not be doing computations on schemes that you don't have some kind of guarantees are going to work. Okay? And this gives you the guarantee you need if you're going to do these iterative techniques. All right, so let's go back and think about the formulation of the matrices we had when we set up those iteration schemes, or at least when we set up the iteration scheme from the first set of governing equations. Here's how they were laid out. So if I wrote the matrix A associated with it, the first equation is here, second equation is here, third equation is here. So let's look to see if this is strictly diagonal dominant, or SDD, strictly diagonal dominant. So I look at the diagonal term as 4, and 4 is bigger than the absolute value of these two terms, which is 2. So that's over here. The absolute value of 4 is bigger than the absolute value of the other two terms, which is 2. So that row works. The next row is 8, right? 8 is the absolute value. It's bigger than 4 plus 1, that's 5. And the next one is 5, which is bigger than 3, which is the sum of the others. So these calculations are done here. So this matrix is strictly diagonal dominant, and that's why it worked. Okay? In the second formulation, where I switched the first and third rows, so basically this here is just this matrix, but where I just switched the first and third row, then I go look at the diagonal. The diagonal is -2. Is it bigger than 1 plus 5? No. Okay, so right away that violates it. The second term, by the way, the 8 is bigger than the 5, and the third, when I go to this diagonal, it's 1, which is certainly not bigger than 5. So this is not strictly diagonal dominant, and that's why we had the blow up of the solutions. So if you're going to use iterative schemes, what you want to do is you want to arrange your governing set of equations into a form like you switch rows so that you can get strictly diagonal dominance. And if you have that, then you're guaranteed to converge with these algorithms. Now, a couple comments. How fast are these algorithms? Right, that's what we're actually asking about. You know, when you set up these iteration schemes, typically what you're going to start thinking about is, well, I've got to update every value, so that's n of them. And then my update rule, the iteration scheme, oftentimes depends on a certain number of the columns. So let's call them m. And generically, if it depends on all the columns, it's n. And then the convergence, how many times it has to run to converge, which is, let's say, k iterations. So your total operation count is something like n times total number of diagonals, or total number of rows it depends on, m, columns it depends on m, and then iterations k. So m, n, k. So what you're hoping to do for very large matrices, because a lot of the matrices we're going to consider that are large come from differentiation matrices which have diagonal structure or dominated tridiagonal structures, which means there's very few of the other columns that matter on a given set of equations, and then this allows us then to actually have a solution technique that can beat both LU and Gaussian elimination in certain cases. Improvements. One improvement to what we did with Jacobi iterations, if we go back to the first successful implementation of this, is that we said the update rule was the next value of x is, you know, here's the scheme, except for now, notice, after I've done this first update, you know, I took the y, the current y and z values to give me the new value of x. Well, since I have a new value of x, sorry, go back here, since I have a new value of x, presumably it's better than the previous value of x, and here then I use it right away. Before I had 4 of x of k here. But now I have a better value of x of k, so use it immediately here. This is called Gauss-Seidel. So in other words, I take this current value and I don't use it at the next iteration cycle. I use it immediately in this iteration cycle. So this pops into here to give me this new value. Now that I have improved values of both x and y, I can go to update z and put in these improvements immediately. So there they are. The improvements are right there. You can put them in. That's where we start doing this, and this is called Gauss-Seidel. And by the way, this converges twice as fast for this simple example as the Jacobi iterations. So again, we started here at 0 iterations. This is my guess. And remember, this took about 19 iterations to get down to these answers, and here it takes 10. And again, we're all about speed. So Gauss-Seidel allows you an improvement that in fact cuts the computational time in half for this iteration scheme. So that's something you'd always want to exploit if you can do so. And so remember, because we're always looking to see how fast can I solve ax equal to b and get the right answer. This is a nice little improvement to the iteration scheme, and you know, it takes me only 10 iterations to get down to the answer. All right, so there you go. This gives us yet another way to solve ax equal to b. We've got Gauss elimination, LU decomposition, and now these iterative schemes. So you can see solving ax equal to b, which is in some sense our #1 priority in this course on beginning scientific computing, it's not just one method. It's a number of methods, and they all give you the correct answer. And the question really then comes down to, why do I have all these methods? And the answer comes down to, how fast can you solve it for a given application? And sometimes you will be using iterative methods, and sometimes you'll be using LU decomposition, and rarely would you use Gaussian elimination unless you're just going to solve one big problem once. But normally both the iterative schemes and LU understand that you're going to solve AX equal to B repeatedly in the course of doing some kind of scientific or engineering design. Again, here's the website for the class. You can download additional lectures, all the notes, and the code used in here to create these iterative schemes. So you can download this and play around.